We now begin our conference with the Institute Colloquium lecture, which is by Dr. Tessy Thomas. Before that, I'd like to introduce her. Dr. Tessy Thomas is the former Director General of Aeronautical Systems at DRDO. She is a distinguished Indian scientist and a key figure in the country's defense research and missile development. She was also known as Missile Woman of India. She made history as the first female scientist to lead a missile project in India and as the project director for the Agni 4 and Agni 5 missile at the DRDO. She also played a crucial role in developing this medium range ballistic missile, significantly enhancing India's defense capabilities. She holds a degree in electronics and communication engineering and began her career in DRDO in the 1980s. And by
Electronics
2019,
and
she
communication
was appointed
wrong.
Director General of Aeronautical Systems at DRDO, which speaks volumes about her efficiency. She contributed to advancing India's aerospace and defense systems and has received numerous honors and awards, including the DRDO Performance Excellence Award and the Lal Bahadur Shastri National Award for her contribution in advancing missile technology. Her accomplishments continue to inspire women pursuing excellence in science careers, technology, and defense sectors. We are very grateful to have such an accomplished personality among us today. I welcome Dr. Tessy on stage to begin her talk.
Yeah, very good evening to all of you. I've already mentioned my topic: opportunities and challenges for women scientists in defense research sector. Defense research provides a platform for innovative research and leads towards technological growth, and basically ultimate purpose is for the national security as far as defense research is concerned. Now we look at uh, women in defense and space research. There are different areas where first we look at the strategic equipments and systems developed in optics, very specific, and then taking the institutions or the organizations like ISRO for space applications, STEM fields, DST and CSIR labs, science and technology development for more of healthcare and industrial applications. Then we have DRDO labs. I think only the Bombay lab is mentioned, NMRL. There are other labs like LRD doing the radar and EW systems, then LASTEC and CHESS, where we do the laser based systems, uh, directed energy weapons, etc. Like in NMRL, also we have the atomic absorption spectrophotometer for material research analysis, elementary level analysis, optical microscope, and scanning electron microscopes. And again, the field of armed forces, all the three services, the application, military applications, we have the optics and photonics. Now, opportunities like careers in cutting edge optics and photonics, leadership roles for major projects. Women are in DRDO, women are in leadership role with respect to technology directors, director of the laboratory, and director general of cluster of laboratories. So if you look at the future, the opportunities in AI and emerging fields are there, and we need to collaborate with the global research networks, and as opportunity there are going to be long term career growth in impactable areas. Now when we say optics and photonics, there are the light matter interaction, the nanophotonics, the transient and steady state spectroscopy, ultra fast optics, nonlinear optics, terahertz generators and applications, These are the fields wherein which scientists do work. And again, the topological singularities, speciality optical fibers, time dynamic systems, disorder photonics, bound state in continuum, photonic sensors are the very many applications. Similarly, industry 4.0, along with the automation, AI and IoT, we have going to see revolutionary changes with respect to optics and photonics. Telecommunication, fiber optics enabling 5G and internet expansion. In defense, the laser based ranging, lidar, optical radar, and laser weapons. Space, remote sensing, satellite communication, and exploration tools. And other the major innovations and breakthroughs are with lasers, getting the ultra short pulse lasers for precision application, fiber optics for global connectivity, photonic integrated circuits, compact, efficient, and scalable solutions. Then comes the future, the quantum photonics, where the quantum communication, the quantum computing, quantum simulation, quantum walks, and quantum metrology. All these applications of integrated quantum photonics. Looking at photonics for the sustainable development, we have energy sector, advanced solar cells for efficient energy conversion, LEDs and organic LEDs. We are talking about Q dot, uh, QLED, the quantum dot, and in environment sessions, we have the optical sensors for pollution monitoring and climate data. Infrastructure, again, the enabling the smart cities with IoT and the data communication. Again, the augmented and real virtual reality and holography, autonomous vehicles, lidars for safe navigation, biophotonics, non-invasive medical diagnostics and personalized treatments, and space exploration, again enhanced telescopes and interstellar communication systems. India's contribution to optics and photonics, if you look, just take an example of space mission, the Chandrayaan. We had laser Doppler velocity meter for measuring velocity during the descent, lander horizontal velocity cameras, laser gyro based inertial reference and accelerometer package, ensuring the lander orientation and the movement. Then the K band altimeter, that's again a laser altimeter, lander position detection camera, lander hazard detection and avoidance camera, laser altimeter in for different height observations. So very many applications are there with respect to the one single mission. Similar is the case with launching a missile, starting from tracking communication. Every element has this optics and photonics. Uh, to say an airborne platforms, we have the EW systems, airborne radars, signal and data processing, subsystems interconnect, data distribution, secure communication, sensors, inertial monitoring units, fiber optic sensors, fiber optic gyros, microwave photonics, health monitoring systems, smart structures. Everywhere the application of photonics is there. I think it is the same thing, put it like cameras and sensors, to what depth it gives the application surveyability to measure the lethality, and lasers for laser range finders, uh, for secure communication. All application, I think, put it across with different applicability and mobility. Photonics is taking a new role in the radar applications where starting from the radar signal generation, we were otherwise hearing about only the microwave, the RF part, photonic up and down converters, signal distribution systems, antenna remoting, echo signal processing with photonic analog to digital converters, optical beam forming network, fiber optic massive data transmission systems. So we are moving into a world of micro as well as at the same time the computational and the efficiency increasing at the same time. A few of the DRDO developed laser systems, if you say, the for light uh, intensity conflict, uh, laser ordnance disposal systems, light detection and ranging, and for Air Force, different applications for the laser guided bomb release and testing, similar for laser countermeasures too. For naval application, again, laser cross section measurement and imaging. I already mentioned about the light uh, intensity conflict, where on ground we can use the laser dazzlers, electro-optic target locators, chemical and biological and explosive material detection equipments. These are already developed by DRDO, the laser ordnance disposal system, as I mentioned. And what I want to mention is that even though we have 10 to 12% women scientists working, but they're all working for every of these systems. Any subsystems you take, any component level you take, there are women scientists working for it. And like optical target locator is another application. Laser dazzler, as I mentioned, it's again a non-lethal weapon for detection of chemical, biological, and explosive agent detection. We focus on uh, detecting the explosive remotely and using techniques such as Raman scattering, lidar, and ultraviolet laser induced fluorescence. Laser countermeasures like laser warning and countermeasure systems for armed fighting vehicles. Components, the sensors, the master controller, the decoy laser, all find its application. And DRDO is into it for making for the three services. Laser threat detection and decoy system, where the threat can be monitored and neutralized by using decoy lasers, safeguarding the key installations, dummy release of dummy targets to misguide the threats. But taking the looking at the challenges, as mentioned that there is materials required for optics and advanced photonics. We need to have materials of like metamaterials and integrating them with the avionic systems and the cost involved for the research and infrastructure. These are some of the limitations or the challenges what we can see, and bridging the resource innovation to practical applications. These are some of the challenges we can say. But as a women scientist, if you look at the opportunities, the uh, the freedom with which you can go ahead in research activities, that is very many and multifold, and need to really tap this opportunity and work for it. So we like growing need for diversity, diverse perspective, interdisciplinary approach today as global and national support, government policies, institutional backing, and rising role models in photonics. I can see the whole galaxy of optics and photonics. Women are all here. Career opportunities across industries, academic research, healthcare, space and defense, entrepreneurship. So we can bridge the gap by going through outreach programs and industry academia partnerships. Vision for future, if you say that research, the areas like quantum, photonics and next generation technologies, very very much of those advanced technologies we need to understand and develop the infrastructure for the research capability, accessibility, making photonic solutions affordable and scalable globally, sustainability, very important in this 21st century where continued focus on the energy efficiency and environmental monitoring is required, inclusivity, encouraging the global collaboration and diversity in the field. I'm sure this 3 days conference is going to leverage the knowledge exchange and global awareness and learning happens during this conference. And I take this opportunity to thank the organizers, Professor Shukla, and all the members, all her teammates, in giving me an opportunity to be here and part of the inaugural session. And I really want to express my congratulations to the organizers for organizing this wonderful thought process of having continuing this being the third women in optics and photonics. So, like what Professor Anita mentioned, that we need to work the like-minded people. So work together, and this is the world where in which the opportunities for this particular field, optics and photonics, is highly going to be highly demanding, and we need to work for this technology enhancements. Thank you for this opportunity to be with all of you. Thank you all.
Thank you, ma'am, for taking us through your journey so far. I'm sure all the young minds have benefited from it. We now have time just for one question. So, may I request Salim to take it to maybe just one question, and the rest we can communicate to her after the session.
I was hoping actually somebody else in the audience would, but I figured I would ask you. In your inauguration time, you mentioned a statement about your own struggle to reach where you are. I was hoping to hear more during your presentation, and I did not. Would you mind sharing just a minute or two on how you got to where you are today through the Department of Defense?
Yeah, it's if you say that going through technology development, first of its kind, in a country where those capabilities or the infrastructure doesn't exist. So we had to really struggle. It's not me alone, it's a group of scientists working for the same cause and purpose. And from starting from design, develop, prototype, test, if it doesn't prove, go through the iteration, all this has happened. And once the projects, when it came to Agni 2 onwards, we started establishing certain of the technologies. Like Agni itself could have thought only by developing a technology called the re-entry vehicle structure. So it goes as high as 1,000 kilometers in altitude and re-enters back with a velocity of 5 kilometers per second. The re-entry vehicle structure goes through a temperature outside of 3,000 to 4,000 degrees centigrade, and the thickness of the structure is something like 23 to 25 mm. And inside, the avionics and the onboard computer and the command control circuits cannot withstand temperatures more than 50 to 70 degrees. So starting from that as the requirement that we need to develop a structure which will withstand 3000 to 4000 degrees centigrade, and within this 25 it should not penetrate the temperature, and it should sustain within 70 degrees. So that capability developing, it took a iteration of more than 10 years to 15 years to develop that. It's again carbon phenolic as the outer layer for thermal protection, where the property of the carbon phenol, it gets charred and remains there. Ablative property, it soaks the temperature but doesn't allow to penetrate inside. It remains charred there. Whereas the carbon epoxy is used as a structural material, structural capability. So within the 25 we could achieve this, and with establishing that technology, we could think that yes, we can go for a re-entry vehicle like long range ballistic missiles, which will go up the atmosphere, comes back with source speed. So that is where the thought of Agni came as a weapon system. Then came the guidance system. I was the person to design the guidance law for all Agni class of missiles. So it is all evolved like one after the other, the technology. That's a great vision of our great visionary leaders, that step by step we were brought in within 15 to 20 years. The total technology was made, and 15 to 20 years, we have seen all the five systems what we planned as tactical missiles, as well as the Agni class of missiles when came in. Then that is we did with Agni 1, 2, and 3. Then came my role as I was designated as project director Agni 4, where and was told that maybe world across is talking about some different numbers of range capability. Agni 3 with 50-ton launch mass, we had 3000 kilometers capability. World across, we're talking about 3500 kilometers. I was a mission designer, also trajectory designer and guidance control. Uh, so I was asked to look at the world class and say design a system, and given the responsibility of Agni 4, and it has to be world class. When we look at the literature, they all use for rocket motor casing, like launch vehicles and all metallic, doesn't matter, weight doesn't matter much on, because it's stationary, launch is from a stationary place and not a field worthy, and it doesn't impact any range because the capability wise. Whereas for us, 1 kg extra will take away 5 kilometers of capability in range. So we used to do weighing in terms of milligrams, the components, the subsystems, wherever it could be optimized, we had to go through. And given a time frame of 5 years, and I was asked to make a world class at that point of time, without knowing what I am shouldering on the responsibility, I said yes. And I never say no to most of the scientific requirements what it comes to me. And I said yes, we can do it. And then looking at is going for a composite rocket motor casing, where the structural weight difference will be of the order of reduction of 40% if you go for a composite. I'm talking of a time where country didn't have the carbon fiber to make for the composite rocket motor casing. So, but NAL was working for it, and we could go through the iterations and came up with thing, and came up with the composite rocket motor. But at the same time, when I looked at one stage of rocket motor alone will not do the thing, then I looked at, as I mentioned, about even a milligram matters. So the from tip of the missile to the bottom of the missile were relooked, reconfigured, redesigned, and we were working on analog systems. Any sensors were analog in nature, actuators, everything we converted into digital systems, and digital communication 1553 bus, all were brought into in the missile technology. And then and finally, when the Agni 4 was flown, it was 22 ton, less than half the mass of Agni 3 with 50 ton, and we achieved 4000 kilometers range capability. So that is the challenges, what I can say. It's all for the, it's all the determination and it's all the responsibility what it is there, and we can do it, we need to do it. So these are the things, and of course within DRDO we are all motivated to do the job. We had very good visionary leaders and the cause is known. We are working for those strategic systems. So that is that's the same there in optics and photonics too also. There are technology leaders who have come up with all-time new systems like radar applications today. If we talk, they are talking about so much of photonics application into the radar systems and all. So that way many things are happening, and thank you once again for this opportunity. Thank you.